It's alive, it's breathing, and it worked. So part of the reason for going through this exercise is to kind of dispel some folklore. So again, some of you are familiar with Babbage and the story of the machine. There's a sort of folklore that states that this machine's design, which is 150 years old, could not have been realized during that period. And you hear that story. So this was designed by one Charles Babbage, who I'll talk about. Design dates back to about 1848 or so, and was never really realized during his day. And so the folklore is that the reason for that is that the mechanical design practice of the time was not sufficiently precise to actually machine the kind of parts that adhere to sufficient tolerance for it to work. However, this machine, although it was built by modern computer-driven milling machinery, it incorporates the level of tolerance that we think was characteristic at the time, so about 1 or 2 thousandths of an inch, something like that. And part of the reason is just the nature of the milling machinery, but also regarding the fact that some, if not many, or all the parts were actually hand finished, and so there's sort of human error that was mixed with that as well. So again, a lot of ingredient. So let's back up and we can talk about what this thing is and why it was designed, what the interest behind it was, and so on. So we have to rewind now a couple of hundred of years or more back to 1791. So enter on the scene one Charles Babbage, born in England, born into wealth. He was what we would call today a gentleman and a scholar. Someone who was independently wealthy devotes his life to some pursuits, a meaningful pursuit. At the time, he was called the gentleman of science. So he was an inventor during the first 30 years or so of his life. He invented all manner of things. For example, the ophthalmoscope. He had some vision problems, and he invented this device to help people like him and help them mitigate their problems. He designed a kind of black box for railway cars, analogous to what we use on jet aircraft today to monitor things that happen after things went wrong. He predicted that someday the world would run out of coal, and so he devised a scheme for harnessing power from tides. So a bit prescient there. He was involved in many kinds of fields, among them astronomy, and one day when he was about 30 years old, he was poring over some mathematical tables with his colleague Herschel. Now, let me back up a little bit, and again, going back to this period of about, let's say this would have been about 1821, what sorts of computing machines do you think might have been available? Any ideas? Anything at all? So, abacus is one thing. Okay, that's sort of impractical for this kind of thing because it would take you so long to do a calculation. Is anything else?
Leibniz was trying to do one in the 1600s.
Machine?
Yeah.
Okay,
He just designed them.
Okay. Well, another thing that was available was the slide rule. Anybody familiar with slide rules?
Oh, yeah.
But so how much precision can you get with the slide rule? It's about 2, 3, or maybe 4 at most decimal digits. Well, to do the type of calculations that were necessary, in fact, you can see in this case, there's a booklet. There's a book of mathematics about logarithmic functions. You can see there are many, many more digits of precision there. To do this type of thing, none of the machines that were available, such as a slide rule, were usually precise. In fact, there were no computing machines as we know them today. In fact, the word computer referred to humans who toiled in manual calculation to produce the kind of volumes that you see there, which were used by engineers and scientists. At the time, there was an explosion of progress in many fields, astronomy, various engineering fields, navigation, and banking. And those fields all required calculations that were dependent on this kind of precision that was only available through the use of these books. Now, to return to what I was saying about Babbage, when he was about 30 years old, he was involved in some astronomy calculations with his colleague Herschel, and he was using one of these books, and he became so frustrated at all the errors that he found in the book that he cried out in frustration, "I wish to God these calculations had been performed by steam." Of course, what he meant in necessarily mean that quite literally, but he meant he wished there had been some kind of automatic machine that would perform the calculations. It turns out this machine does that, and I'll explain that. So at that point, Babbage devoted the rest of his life to designing calculating machines that could do the types of things that humans did in an automated way. So now rewinding again to about 1821 or so, at the time there were no computers, there were no automatic systems of machine design, there were no 3D CAD packages or workstations, as we just discussed. In fact, there was no system for screw thread convention. There was no systematic way of managing mechanical tolerances. In fact, there was not really a notion of interchangeable parts at the time. So the first thing that Babbage did was he toured the European continent and he surveyed the best practices, not only in mechanical design, but drawing and so forth, all related fields. And he came back, and one of the first things that he did was he invented his own system of mechanical drawing, and he invented approaches to managing screw thread parameters and all that kind of thing. And then spent maybe a year or two or something like that doing that, and then launched the designs of these machines. So I like to sort of categorize his computing machine or calculating machine designs into three major categories that I call Babbage 1, 2, and 3. This is Babbage 3. So going back, Babbage 1 was a calculating engine, which is this is, which basically would have done the same thing as this, but it would have been far less efficient. It would have been about 3 times the size and weight and complexity. So about 15 tons versus 5, about 24,000, 25,000 parts versus 8,000, and 3x the size, so about the size of a railroad car. So he began his first design, Babbage 1.0, or the difference engine 1, with some help from the British government. So he was able to secure about 17,500 pounds, which is not very meaningful today, but at that time, that would have been enough to buy you about 22 brand new steam locomotives. So he set out building his first design. He worked on that for about 11 years, about 10, 11 years, and he produced about half the parts, so about 11,000 precision parts. At that point, he got into a disagreement with his toolmaker over moving the factory closer to his home, and everything stopped. In fact, all the 11,000, almost all of the 11,000 precision machine parts were melted down for scrap. Now, as you can imagine, the British government was not happy about this, but as it turns out, there was no formal contract between the parties, and so everything just sort of stopped. So that's, of course, very disappointing in many ways. It's disappointing in retrospect, but the good news is that freed Babbage to go on to his 2.0, which is also called the analytical engine. Now, instead of just being a calculating kind of apparatus, that design was a true computing apparatus. So it managed floating, rather multiplication and division. It was a programmable kind of design. Would have used punch cards for programming, like much more modern machinery. Used systems of microcoding and so forth. So a very, very advanced design. In fact, embodying many concepts that were implemented really only recently, in the last few decades. In fact, it wasn't until about 1970 that people really unearthed his designs and realized that many of the things that he invented in the 1800s were thought to have been invented more recently, but were really pre-existing concepts. So he worked on the 2.0, the analytical engine, for something like another dozen years or so. And being an inventor and being really a genius, he got into all sorts of tangents and looked at all sorts of variations in this machine. And really this 2.0, or the analytical engine, was really many, many different designs. In fact, it's interesting to note that he wrote in his logbook one day something to the effect, in paraphrasing, I basically got it, it's basically complete, all I need to do is finish a few drawings and it will be done. And he spent perhaps another, well, the rest of his life actually, another perhaps several decades working on advancements of the designs. So at one point, having developed the analytical machine to a certain point, he realized that he could have designed his difference engine, the 1.0 design, much more efficiently, in fact, about 3 times more efficiently. And so he started working on 3.0, or the difference engine number 2, which is this design.